All right, now we're going to take a brief look at some current mirrors. Um, but I did want to say first, that last video I was talking about available constant current sources, as far as tips are concerned. And, I showed you a couple of them, but I forgot to tell you that most of the others, even in surface mount, are all based on the LM334Z. I mean, I just really couldn't find many that weren't. There are all some variant of that, and the part number proved it. So, those 334Zs are neat, but they're so finicky, with temperature. They're actually used and recommended for use as a temperature sensor, if that tells you anything. So that's one of the reasons I'm kind of wanting to, find other constant current sources. So, that at least something with discrete components, you might be able to frickin' do something about the temperature. Compensate it with, 15 part per million, resistors or something like that. Which are actually pretty cheap. I mean, you can pick those up, at Mauser, for like 25 cents a piece in single unit quantities. So it's, but it's just something to be aware of that, um, that there just really aren't many options available. Those two I showed you, I think, are temperature compensated. At least one of those said it had a band gap reference in it. But barring anything else, I mean, it's just, again, you're stuck with either op amps, which are still going to have temperature dependencies, probably not as bad as that 334Z, though. I mean, there just really aren't, there really aren't many options when it comes to CCSs. So it's, you know, um, like I make this note here, you might read that, it might be beneficial or it might help. I'm hurt, because especially on the SPET circuit, I mean, I'm not sure what the temperature performance on that is, but, it's going to have an opposite temp, co to the transistor, so they might offset each other a little bit. I have no idea without running a temperature test, but I got to move on. So, um, but you might be able to get some NTC resistors, that have negative temperature coefficients, and maybe that could offset some of that. Because especially in a purely transistor version, but even the one with the FET I showed you, you're going to get variations in, in beta. Beta increases, as temperature increases. So, it might be beneficial to have a resistor that, I don't know, decreases or something, to kind of offset that. Um, so that might improve the temperature performance. And again, all around, for at least for your references and everything, using 15 part per million instead of 200 part per million, resistors may improve things too. It'd be an interesting thing to test, but I don't have resistors like that in stock at the moment. So anyway, without further ado, all right. So basically, I've breadboarded, this little constant current mirror together, and see, one's a control. This is a control transistor, and that's the controlled transistor. That mirror. This current mirrors this current over here. Um, Now I made a few changes. Instead of using 10K resistors on each of these, I use 3.3K resistors on them, so I can get a higher current range. Get a higher current range out of it than he has. Um, and basically in my control transistor, I also got my decade box um, hooked across it. Hooked in series with it, and ammeters on both channels. So I don't have a voltmeter on the circuit this time. This is all strictly about current. So, basically, let me move this over here, and increase the size here. Yeah, but basically we got the circuit right here is the current mirror. So those are 2 transistors. Now, this one right here is my control transistor, so I use a 0 ohm jumper to short between them, and this is the controlled unit I got hooked to my fluke. So the O1 has got is measuring the current of the control, whereas the fluke is measuring the current of the controlled. So basically, when I change the current when you see the current change on this one, it's being reflected on that one, at least with considerable error, although I still can't discount the possibility the 2 instruments have different performances as well. But like I said, I got my little decade box here, and I'll just go through a bunch of different resistances, including, let's start with the maximum current that just, because I only got this running at 15 volts, just to, it's adequate to test it. So that, that's about the maximum current, with no settings on the decade box. So, about 4 milliamps, is what you get, and there's certainly a little discrepancy there between these two, about 40 microamps or so difference. So, but let's start changing it. 400 ohms, so you can kind of see, how these things track. 1K. And see, they do quite, get, there's some pretty good disparity between these two, but, a couple hundred microamps right there, theoretically, assuming they're both valid readings to begin with. You see, the fluke is smoke damaged, and O1 as well, it's, Chinese, so, but anyway, yeah, you see a pretty good discrepancy between these two, but it is the simplest form of current source. But yeah, I can even load this thing up, with over 100K right now. So you can see that the smaller the current, the more accurate they appear to become. Even though really you're just running out of resolution on your equipment, it's more likely the culprit. But yeah, that's 22 microamps of current. Let's take it up to 400K plus. Okay, 14. Put 1 meg at it. 7.3. Put 4 meg additional on it. So yeah, 2.3, 2.4. They seem to track each other pretty well, and you can kind of see, that I've flipped half the switches on this thing. So, so we got, 1 meg, 100K, 200K. So that's 1.3, 1.6, 9, and throw an additional. So it's like 5.9, and then and some change here, so it's certainly over 6 meg. So it's actually interesting. So the thing is that there's more elaborate versions of this too that he's got here. He said you can get rid of some of the discrepancy by putting this transistor here, but on the other hand, he's talking about base currents, and we're seeing a lot more than just base current discrepancy on some of this. So however, this version down here might actually improve the accuracy. It might match it better, but I don't think I'm in the mood to mess with it right now. Because I just got done pulling my hair out on those stupid constant current sources for the last 2 or 3 days. So I'm just kind of anxious to move on at this point. But anyway, this article is still a good read. Even though, as I've demonstrated, you may have to take some of this with a bit of a grain of salt, but just talk about a number of things in it. It's current sources, sinks, etc. So, Elliott Sound Products. Just look for that article. In fact, you can just Google this and Elliott Sound Products, or ESP as he calls himself, and you can probably find it easy enough. At any rate, But this is just the most comprehensive document I've ever seen on constant current sources, which, it's still not anywhere near perfect. I mean, I'd certainly like to see more information on some of these things and what the pitfalls. I mean, why don't you see these simple little constant current sources very often? Because as I've demonstrated, they actually, when they work properly and aren't crapping out and doing weird shit on you for some reason, but maybe somebody knows what the weird reasons are for some of that. But they're actually pretty decent little current sources. Overall, I'm shocked how well, particularly they do, particularly with that 2 transistor version I did. That was way better than that FET version, even. I mean, that was really impressive. I guess that shows you what the benefits of matched transistors are. But I just got lucky on that one before they, I blew them out. By short circuiting the terminals. But anyway, I think that'll, about cover, the constant current sources for the time being anyway. So I may look at some off-amp ones later on, maybe, but for right now, as far as simple constant current sources, I think that'll about wrap up the show. So cheers.